Chapter 1 Introduction to Physical Geography, Section 1.5 Systems Theory and Science. Systems theory is a methodology that was invented in the 1940s that allows people to study and better understand natural things. It begins by defining what is a system, and a system is defined as a group of parts that work together through some kind of process. Systems theory is also used in computer science as a way of understanding how programs work. Systems generally have a boundary, they exist in the boundary, and within that boundary we can find three kinds of properties: elements, attributes, and relationships. So let's think about a system in terms of a simple setting, an aquarium. Let's pretend an aquarium is a system. Now, an aquarium has elements or things or parts making up that system. In an aquarium, you could have fish, water, they need that to swim in, and aquatic plants. An attribute is a characteristic of one of the elements that can be measured. So, for example, in terms of fish, we have guppies, we have mollies, and we have, let's say, maybe a catfish. So those are characteristics. They're the different species or types of fish that exist in the tank. Then we also have relationships. Relationships are cause and effect relationships that exist among the elements and their attributes. For example, the water. The water has to be the right temperature for the fish to survive in. If the temperature goes too high, the fish will die. If the temperature goes too low, they will die. Systems can also be expressed mathematically or by a diagram or let's say a model is what I'm trying to get. They can be a model is a type of system. Models can be mathematical. They can be a diagram showing the parts, or they could be like a model car that you put together. Little parts that represent the big parts, just in miniaturization. Here's an example of a system, and this is a system that I've created to try to help you understand how the Earth is powered. And I'm suggesting the Earth is powered by the sun. The power that is received by the Earth comes from the sun's surface in the form of sunlight. At the sun's surface, the intensity of this sunlight is 64 million watts per meter squared. It travels across a huge distance of space, and as it travels, it becomes diffused. By the time it is intercepted by the Earth, that sunlight is now reduced to an intensity of 1370 watts per meter squared. As I said, models can be illustrations, scaled down representations of something, or a series of mathematical equations. And humans have devised a whole bunch of models in the form of mathematical equations, and we run these models in computers to create simulations. And probably the one that you deal with on a frequent basis is a weather forecasting model. So meteorologists have devised these models, and they input data, current weather data, and from that they can predict what the weather is going to be like in the future to a certain number of days into the future. And for a period of 1 to 5 days, these systems are pretty accurate, and they do a pretty good job in determining what the weather is going to be like in the future. So this map here represents the output that is produced from a weather forecasting model, and of course a meteorologist then interprets this and suggests, oh look, there's two high pressures in the center of North America, and there's a mid-latitude cyclone low pressure system off just north of Florida. There are many different kinds of systems, so I'm going to describe here three types. An isolated system is a system that does not have connections beyond its boundary. So let's say a chemical reaction that's occurring in a test tube. That test tube, the glass edge of that test tube is its boundary, and really nothing occurs outside that boundary. Everything's occurring within the test tube. Closed system does not allow matter to cross its boundary, but it does allow energy. The Earth can be considered a closed system, that we're not really gaining that much matter, maybe a few meteorites, but for the most part space doesn't contain much, and we're not gaining much in terms of the Earth, but we are gaining energy from the sun, and that powers the atmosphere of the biosphere. An open system has both matter and energy crossing its boundary, and an example of an open system could be a pond, and I'll show a picture of that in just a second. The other thing that's interesting about systems is they usually have a hierarchical structure that is connected and functional. If you consider your body to be a system, you've got chemical elements that construct small things inside your cells. You've got the cells that connect together to form tissues. You have tissues that form organs, and those organs are in your body. So a human body has a hierarchical structure, and there is connection to the various levels. So once again, here's our picture of a open system, a pond. So it's getting energy from the sun that's causing the plants to grow inside that pond and the algae. It's also gaining matter in the form of rainfall and debris, plant debris falling into the pond. So it's an open system. The Earth, it would be an example of a closed system. So really we're not gaining in any significant amount matter, but we're gaining vast amounts of energy from the sun 24/7. Now, an important concept related to systems is the concept of equilibrium. And equilibrium is the measurement of some sort of attribute related to an element, or it could be the measurement of a relationship. So related to equilibrium is something called the system state, and the system state is defined as the current condition value of an element, attribute, or relationship in a system. So, for example, the system state of my heart, I could measure an attribute being beats per minute, and I get an average value of 72 beats per minute. The condition of system state can be measured over time, and the pattern that we see over time is called the equilibrium, or the average condition. Now, several different average conditions exist. I'm going to describe 6 of them. So on all 3 of these graphs, on the x-axis we're measuring time, and on the y-axis is the measured state, whatever thing that we're measuring in a system. The first graph shows what is known as a steady state equilibrium. The red dotted line represents the average state. We see it doesn't change over time. There are fluctuations. The black line represents the actual measurements, and when you average them over time, they stay the same. A dynamic equilibrium has no average state. It's completely random what takes place over time. A thermodynamic equilibrium usually relates to energy or matter in a system, and it's believed the usefulness of both this matter or energy declines over time until you reach what's known as maximum entropy, so maximum uselessness of the energy or matter in a system. The universe is considered to be in thermodynamic equilibrium. The sun would also be an example of thermodynamic equilibrium. The amount of energy that's produced from its surface is going to decline over time until it's all used up. A static equilibrium is where the average state doesn't change. It just has the same value over time. A stable equilibrium is a system where you get a disturbance. So we can see in this slide, there's the location of the disturbance event. The system state changes, and then it returns to the previous pre-disturbance level. The last graph shows an unstable equilibrium. So once again, we have a disturbance event. Before the disturbance event, you have a certain level in terms of the measured state, the equilibrium. The disturbance event occurs, there's a change, and then it returns to a new measured state. So, for example, COVID is a disturbance event. The number of people, let's say, doing air travel per day was much higher level. COVID hit, regulations and other things were put in place, and now we have a much lower level of people traveling by air. That's the end of this lecture.